A lone photon can cross the cosmos forever and never age. For light, the elapsed proper time along its path is 0. It moves at light speed, so time dilation goes to infinity. From our view, that photon can take billions of years. For the photon, the trip has no internal ticks at all. Does it fade, lose energy, or get trapped by gravity? Today, we will follow one photon from birth to eternity. You will see why forever does not mean what it seems, and why the universe keeps changing that photon step by step. In plain terms, light's own clock never advances between emission and absorption. Think of a photon as a packet of electromagnetic field energy. It has no rest mass, so it always moves at light speed. Its energy depends on frequency, through Planck's constant times frequency directly. Wavelength and frequency trade places, because C equals frequency times wavelength. Now for the geometry that sets our intuition straight today. In relativity, distances in spacetime carry a sign that changes intervals. Paths with light speed have 0 proper time between endpoints exactly. That does not mean the photon has its own rest frame. A rest frame for light does not exist in physics today. It simply means nothing ages along that light-like worldline segment. Why should you care about this abstract-sounding rule today? Because it explains how a photon can travel forever unchanged internally. Its phase advances, but no internal clock says a second passed. External stuff still acts on it, like gravity or scattering. So the story is about interactions, not the photon's own aging. Picture a straight worldline bending near mass, yet remaining light-like throughout. Every bend redirects momentum and can shift observed energy as well. What counts next are the places the photon passes through. Sparse gas, stray dust, background light, and curved spacetime itself. Those decide whether a photon survives, fades, or gets redirected, and that is where the universe starts editing the beam. Keep that in mind as we send our photon onward. Between galaxies, space is not empty, but it is sparse. Think a few hydrogen atoms scattered across a cubic meter. Occasional dust grains drift like tiny soot through the dark. Starlight and infrared glow fill space as a background fog. Physicists call that the extragalactic background light, or EBL. Our photon meets these, and each carries a small chance. Scattering redirects it, absorption kills it, conversion spawns pairs, but the odds per step are tiny for most energies. Across megaparsecs, tiny odds add up into real attrition. Numbers help anchor this, so here are 2 guideposts. Optical photons often cross billions of light years without a hit. TV gamma rays barely make hundreds of millions of light years. They collide with starlight photons, then produce electron-positron pairs. Radio waves interact even less and can cruise astonishing distances. Microwaves from the young universe still bathe us today. That bath is the cosmic microwave background at 2.7 Kelvin. It has crossed 13 billion years without being truly absorbed, so our photon is probably safe if it rides low energy. It gets dimmer in energy but rarely vanishes completely. When it does vanish, it usually feeds charged particles instead. Those particles radiate again, sending the energy onward as cousins. Energy flows, identities swap, but the universe keeps the accounts. That bookkeeping is conservation, and it never takes a break. Our photon survives when those conservation options are simply not triggered. Space itself stretches, and that drags light's wavelength with it. As the scale of the universe grows, each crest spreads wider. Frequency drops, so energy drops because energy tracks frequency directly. This is cosmological redshift, not motion through space like Doppler. Light keeps speed c, while its color slides down the spectrum. Numbers make it plain, so compare 2 cosmic snapshots. At recombination, the universe glowed near 3000 Kelvin. Wien's law gives a peak near 1 micron, like deep red. Today, that same light peaks around 1 millimeter in microwaves. Scale factor grew by about 1,100. The wavelength grew by the same factor, and energy shrank accordingly. That trend continues forever in an accelerating universe like ours. Double the scale and you double the photon's wavelength. 10 times more expansion, and the energy drops by 10. Eventually, a visible photon cools into microwave, then radio. Give it more time and it slides to kilometer wavelengths. Its energy becomes so tiny, it is functionally undetectable. By then, no telescope can collect enough cycles per lifetime. Locally, observers just watch the color drift, while the speed stays. Globally, growth of space writes zeros across the energy ledger, so a photon that travels forever becomes colder than any cryostat. Stretch the wave with every breath of space and watch color fade to ember, then to ash quietly. The ripple keeps moving, while its energy thins into near silence, across a universe still making more room. Gravity does not slow light, but it does bend paths. Mass curves spacetime, and light follows the straightest allowed line. In curved space, straightest means a geodesic through warped geometry. Pass near a galaxy and the photon arcs like glass. We call that gravitational lensing, and we see it often. One source can appear as arcs, rings, or multiple images. Different routes take different times, even though speed stays see that time delay shows up as days between image flickers. Climb out from a deep well and energy redshifts. Drop toward mass and energy blue shifts to higher frequency. Close to a black hole, the path choice becomes binary. Aim inside the capture cone and the photon never returns. Skim outside that cone and it slingshots with new direction. Either way, proper time remains zero along the whole track. What changes is energy measured by observers in different places. A lens can brighten the photon, but never create energy. It just steals light from a wider area of sky. Our traveler survives, but its course is braided by gravity. That braid is how we map dark matter without seeing it. Delays, arcs, and magnifications sketch the mass hidden in halos. Light writes the map while never slowing down for anyone. Forever sounds simple, but cosmology sneaks in a twist. An accelerating universe builds an event horizon around every observer. Beyond that boundary, light emitted now can never reach you. For us today, that distance is about 16 billion light years. As expansion continues, that horizon stays and distant galaxies vanish. Locally, the Milky Way group remains bound while everything else recedes. A photon launched outward from us might never cross back in. Launched inward toward us, it must start within the horizon. Otherwise, its waves stretch faster than the catch-up can manage. Mathematically, its energy decays roughly exponentially with cosmic time. Physically, that means colder, redder, and fewer detectable cycles. There is also a faint horizon temperature from quantum effects. It is the de Sitter bath at about 10 to the minus 30 Kelvin. Our photon redshifts into that bath, becoming part of the hush. It is not destroyed, it just becomes impossible to extract. Meanwhile, black holes wait as one alternative final destination. A small target, yet eternity supplies tries without any rush. Should it fall in, the story converts to horizon bookkeeping. From outside, that energy eventually leaks as Hawking radiation. So forever really means either redshifting into silence or meeting a horizon. Both outcomes respect conservation, while erasing practical chances of detection. Energy changes the gauntlet our photon must run. At the low end, radio simply cruises through the fog. Rayleigh scattering fades out as wavelengths dwarf tiny particles. Absorption lines miss because atoms cannot bridge such gentle gaps. Move up to optical and dust begins to matter. Grains soak light and re-emit as warm infrared glow. On galaxy scales, that is why nebulae sometimes hide stars. Push to gamma rays and the background fog fights back. Two photons can annihilate into an electron and a positron. That process switches on when their energies meet a threshold. Multiply the energies and compare with electron mass squared. With CMB photons at about 6 times 10 to the minus 4 electron volts, the threshold sits near 400 teravolts. Using optical background photons at about 1 electron volt, it is hundreds of gigaelectronvolts. So TV gamma rays rarely cross a gigaparsec in one piece. When they collide, pairs form, then secondary cascades light up around. Magnetic fields stir the cascade, spreading energy across the sky. Back down in X-rays and optical, most photons do survive. They may scatter once or detour through a lensing arc. Many reach us from redshifts beyond 10, carrying newborn galaxy light. Their spectra arrive stretched, but their arrival is unmistakable. Energy thus sets survival distance and sculpts a cosmic horizon. Low energy wins the marathon, while high energy burns bright early. How do we even know any of this is happening? Because our detectors are time machines that count ancient light. A radio dish gathers meter waves that left quasars eons ago. A cryogenic bolometer senses microwaves from the first neutral atoms. CCD arrays sip red photons stretched by expansion since reionization. Each pixel records a count, a place, and a time. Statistically, we reconstruct the journey those photons likely took. We compare energies, directions, and delays across many sources. Observers see lensed echoes with day-long delays in active galaxies. Gamma ray maps show gaps where pair production eats the beam. The microwave sky is nearly uniform, yet rippled. Those ripples seed galaxies, and our detectors can measure them. Cross-checks across wavelengths make the story cohere cleanly. The same photon bath appears in radio maps and microwave spectra. Calibration keeps us honest, because instruments love to hallucinate ghosts. Blank fields and cold loads set our noise floors carefully. With care, a handful of counts becomes a cosmic biography. That biography says photons are stable, but never untouched. The journey writes on them, and they write on our sensors. Together, those marks reveal what happens when light travels forever. So that lone photon can fly forever and never age. Yet the universe keeps lowering its energy and bending its path. It either fades into the horizon hush or meets a hole. From our side, forever ends when detection becomes impossible. That is the quiet punchline behind our opening claim. Light's own clock stays still, while everything else keeps editing. If this changed how you picture time and light, stick around. I have more cosmic stories that reward curious minds. Tap subscribe and let's keep traveling together. Next time we will chase a neutrino across the abyss. Thanks for listening and for bringing your curiosity tonight.